Next exercise, number 5 of this sheet. This time it's a volume integral just of the, well, you could say regular sort, without any need to perform a coordinate transformation, at least for the first part, which we may easily carry out in Cartesian coordinates. The second part will be a little different. There, spherical coordinates come into play again, but it will be interesting also to see how they are set up. Well, now for the first part, we are asked to calculate the total value of a certain scalar function f of x, which is given here, whatever it means. And this function of all the three spatial variables x, y, z is defined everywhere inside a certain cuboid. It's almost as simple as the cube. So it's a cuboid, the figure here, which is given to extend from the origin to, as a diametrically opposite point P, to this point in space, which has the coordinates pi for x, pi half for y, and 1 for z, which means, in other words, that this is a, well, it's a little bit similar to the previous exercise, so that one of the corners of this cuboid is in the origin, and the one diagonally opposite is this one. So it's quite obvious that the x variable therefore ranges from 0 to pi, the y variable from 0 to pi half, and the z variable from 0 to 1. So that's just another way of saying this. Okay, you see, so this is the range. And if I right away, if I set up an iterated integral for the three coordinates from inside out, z, y, and x. So this is what I may do, because the limits are independent from each other. It does not play any role, or it does not matter in which order we perform these integrations, actually. But I decide the inside integral here to be referred to the z coordinates. So here the limits have to be from 0 to 1. So, you know, we go from inside outward, and then the second differential refers to the middle integral from 0 to pi half for y. And, well, the last one only refers to the x coordinate, which runs from 0 to pi. So this is the term. And if we integrate over z first, we note that we have to handle x and y as to be constants. So this is just a factor of cosine of x plus y, which stays there. But then, on the other hand, the primitive function of e power 3z has to be taken, of course, referring to z. And as we all know, this is just a case for a linear substitution, which we don't even have to write down. We remember that it is sufficient in this case to divide by the inner factor here, which is 3. So we just take a prefactor of 1 over 3, and then we integrate the exponential function to its primitive, which is the same as itself. Okay, so e power 3z stays there, but we have to divide by 3 for the, well, just to correctly, regard the inside factor here. That you can easily check by the chain rule that the derivative of this term gets you this integral, this integrand function again. So that's our primitive function for z, and we may and we should right away insert the limits from 0 to 1. So if we do so, we get 1/3. Well, we can even leave this away. E power, we can just put it there, the factor of 1/3, okay? And then evaluate e power 3 times 1, which is e power 3, minus the value at the lower limit. But don't forget, e power 0 isn't 0, but instead it's 1. So we have to subtract 1 here in parentheses. So then we may go on and integrate this term with respect to y. So please still treat x as a constant, and then recognize that anyway, the cosine has a primitive function which is sine of its argument. So the argument stays x plus y. But then, well, theoretically, we would have to perform sort of a, say, substitution before we do this. Now, but this time the substitution is unnecessary, even if we treat x as a constant. We have the sort of a linear function here, which is sort of like a plus, or no, let's say, well, b plus a times y, where y is our variable. So this is a so-called linear inner function again. And if this linear factor, this factor of a equals 1, as it's the case here, we do not need to do anything to account for this inner function. So if you compare it with the step before, here we had to account for the factor of 3 by dividing it. Here we do not have to do anything. We just take the primitive function of cosine to be sine. But then, okay, of course, next step, we have to insert the limits for the y variable, which are 0 and pi half. And of course, as always, I will insert pi half first. For y, please leave x alone. So, and then subtract the value of, of this term at y equals 0. So inside here, I get sine of x plus pi half first, minus sine of x plus 0, which is just sine of x. And this whole term may easily be transformed, as you see, as you remember, this corresponds to a left, well, to a displacement of the sine curve to the left by a value of pi half. And as you all know, it changes to be a simple cosine of x in this way. So that's a simple connection, well-known relation between sine and cosine. The sine of x plus pi half is exactly the cosine. So that's quite comfortable at this place. You also know that the sine of 0 is 0, while here the sine of, if I take x equals 0, I get sine of pi half, which is 1. And this is characteristic for the cosine function, that its maximum sits at the position x equals 0. So that's a good way of testing it. Now, you remember this is just a factor we got before, which is constant and may stay outside. But then the last step, we have to integrate this resulting term over x also. And so nicely, we get the primitive function of cosine of x, referring to x, which is sine of x here, you see it, while this sine of x has a primitive function of negative cosine of x. So, but then that means that minus sine of x gets integrated to be plus cosine of x. So everything's positive here. And then evaluating last time, inserting pi for x. Now, of course, gets us, well, carefully look here. The sine of pi, of course, is 0, but the sine of pi is 0, but the cosine of pi equals -1. That's its minimum, right? So we get -1 at the upper limit, and then we have to subtract the value at the lower limit. Please don't make a sign mistake here. And while the sine of 0 is 0 again, the cosine of 0 equals 1 this time. So we get -1 as a value, -1 as a value on the lower limit. In the end, -1 minus 1, which is -2. And if we draw this together, we get a result which is -2/3 times e cubed minus 1. So some people might have the idea to say, okay, this is not the nicest form. I can take this minus sign away, put it inside the parentheses, and then I can write 2/3 times 1 minus e power 3. This is actually not a good idea, I think, because in this way, it appears at first sight, it appears to be positive. But then if you look inside these parentheses, you find out this is a negative term. You may do this transformation, it's no problem. But I did not do it on purpose. The purpose is to explicitly make it visible that this is a negative result. Actually, it is, because now in my parentheses, this is positive. But anyway, the result of this exercise is negative, which is due to the fact that this function term has, well, you could say that inside this cuboid, there are quite large regions where this whole term is negative. So the total result is even negative itself. That's it for this part. And let's look for the second one shortly.